Hello and welcome. In this video we'll take a look at a couple of examples of solving a system of linear equations by the method of elimination. So there are some minor differences in the operations that we perform based on the equations that we're given. So for example, here in this first example on the left, our first equation, we see that in order to cancel out the 2x here, we would need to take a fractional multiple of 4. Specifically, we would need to take negative 1/2 of 4x plus 3y equals 9 and add that to 2x plus 6y equals 10. One of the other things that we can do is we can decide to switch the two equations because the order in which we consider them really is not important. So if I write 2x plus 6y equals 10 and then I write 4x plus 3y equals 9, we see that it's still the same two linear equations. So ultimately, the solution is going to be the same. They're still going to intersect in the same spot, but this gives me a better pivot. So I like to use the word pivot, and you'll see that a lot. We're going to use the second equation as our pivot to help us cancel out the x components. And this is just for convenience. We could have taken negative 1/2 of the first equation and added it to the second. So what I'm going to do here is I'm going to take negative 2 times the first equation and add it to the second one. Now remember, we're not actually changing the first equation, we're just using it to help us eliminate something in the second. So what this would give me is, first of all, I'm going to go ahead and just copy down the first equation because I'm leaving that one unchanged. And I'm just using it to help me cancel something out in the second equation. So if I take negative 2 times 2x, it gives me negative 4x, plus 4x gives me 0x. You'll soon see why we're keeping track of the 0x. It is really important because when we work with it in matrix form, we have to have placeholders for all coefficients. Negative 2 times 6 is negative 12. Negative 12 plus 3 is negative 9. So we have minus 9y. And negative 2 times 10 is negative 20. Added to 9 gives me negative 11. So I took negative 2 times row 1, and I'll write it like this, negative 2. And I'm going to refer to them rather than equations as rows. So the first row is really the first equation. So we took negative 2 times row 1, and we added it to row 2. And that, in effect, became the new equation for row 2. So this arrow here just indicates where that result is going. So we took negative 2 times row 1, added it to row 2, and then adjusted row 2 to be the result of that. Now what we're going to do is, we see that the second equation allows me to isolate y. So what I'm going to do next is I'm going to take, to cancel out negative 9, I have to divide by negative 9. So that would be the same thing as saying take negative 1/9 times row 2. And of course we're going to put that result in row 2. This arrow is not super necessary as long as the second row that you have listed is the one in which the result goes. But this is kind of telling us what we're going to end up affecting or what we're going to end up changing. So negative 1/9 times the second row. Well, negative 1/9 times 0 is 0. And before I do that, I'm going to go ahead and just copy down the first row here. Negative 1/9 times 0 is 0. Negative 1/9 times negative 9 is 1. And negative 1/9 times negative 11 is 11/9. Okay, so this is where, elimination is not super fun because when you end up with fractions, you do have to keep track of them. It's good to have some sort of calculator handy, whether that's a graphing calculator or some sort of web-based calculator that allows you to keep things in fractional form. So we could approximate it at this point, but we want to avoid rounding error, especially when we deal with bigger systems where that rounding error can really start to accumulate. So now that we have that, we're good. We've really solved for y. We know that y is equal to 11/9. So I'll just put a little star here and I'll say that y is equal to 11/9. So we know that. Now this is very tempting at this point to take 11/9, plug it into the first equation and solve for x. And that would normally work. But when we're going to convert to matrix form to do this way more efficiently, we're not going to actually use substitution at all. So when we're using elimination, we want to stick with it. So now what I want to do is I want to, in the first equation, eliminate the y and have that equation tell me what x is. So I see that if I take negative 6 times the second row and add it to the first row, that will help me cancel out the y. And that's exactly what I'm going to do. So I'm going to take negative 6 times row 2, add it to row 1, and report that result inside of row 1. So we're going to take negative 6 times this row. And of course, the one important thing here is that we don't start doing this until we have this 0 here, because if this wasn't a 0 and we added it to the first row, then we'd be changing the x coefficient as well. So negative 6 times 0 is 0, added to 2 is still 2. Negative 6 times 1 is negative 6, added to 6 is 0, so we have 0y now. And negative 6 times 11/9 added to 10, well, that's the tricky one, so let me come back to that in a second. Second row does not change at all. We're already done with the second row because that has given us what y is going to equal. So we have 2x plus 0y equals, and now I need to take negative 6 times 11/9, which is negative 66/9 added to 10. So I'm going to come to my calculator, negative 66/9 added to 10, and it comes out to, you probably can't see this, but about 2.7, and then I press my math button, convert it to a fraction, and I get 8/3. So this comes out to 8/3. Okay, so we're almost done. We see that 2x is equal to 8/3, but we don't want 2x. We want to solve for 1x. So to make this into a 1, I can take 1/2 of row 1. So I'm going to take 1/2 of row 1, and I'm going to store those changes back into row 1. And we're almost done here. We just need to conduct that. So 1/2 of 2x is 1x. 1/2 of 0 is 0. 1/2 of 8/3, well, let's see, 1 times 8 is 8, 2 times 3 is 6, so this is going to be 8/6 or 4/3. And so I get 0x plus 1y equals 11/9. So there we have it. So we see that x is equal to 4/3, y is equal to 11/9, and we can report our answer as an ordered pair and also as a vector. So 4/3, 11/9, or in vector form, we could say 4/3, 11/9, like so. The last step we might want to engage in is just to check our work, make sure that the solution we found does in fact satisfy the equations. And so if I take 4 times 4/3 plus 3 times 11/9, I should get 11. So let's see. This is 16/3 plus 33/9. And let's see, that's going to be... Now, you can just go ahead and input this into your calculator and double check. I'm just showing you all the fractional work here. This is going to be 48/9 plus 33/9, which is 81/9, which is 9. And therefore, since the left-hand side is 9 and the right-hand side is 9, we know we've satisfied the equations. Similarly, I could take 2 times, I have to be able to take 2 times 4/3 plus 6 times 11/9, and I should get 10. And I'm just going to jump the gun here and say that we do in fact get 10. So we've correctly solved this system of equations. Now our second system, we can already see that we're dealing with 3 and 2 here, so we're going to have to deal with either thirds or halves. In this particular case, I prefer to work with halves. So it's easier to take 2 and multiply it by the right number of halves to get 3. So once again, what I'm going to do here is I'm going to go ahead and switch these two equations. You don't have to. You could take negative 2/3 to cancel out the 3's. Negative 2/3 times 3 is negative 2, and add that to the second row. But I don't want to work with thirds personally. I'd rather work with halves. So I'm going to go ahead and list the second equation first. Remember, we're not changing the system here at all. All we're doing is we're just creating our problem in such a way that it makes it a little bit easier on us. Okay, so I see that if I take negative 3/2 of the first row. That will cancel out the 2's and leave me with negative 3x, so I want that. So I'm going to take negative 3/2 of row 1, I'm going to add it to row 2, and I'm going to leave that result in row 2. There we go. So negative 3/2 times, oh, and I'm going to leave the second equation the same. I'm not changing the second equation. Oh, I am changing the second equation. Sorry, I'm not changing the first equation. I'm just using it to help me cancel out the x in the second equation. So negative 3/2 of 2 is negative 3. Added to 3 is 0. Negative 3/2 of 3, let's see, that's going to be negative 9/2. Negative 9/2 added to 2, that's 4/2. That's going to be negative 5/2. And again, you can do this all in your calculator to help you work with the fractions. I'm just kind of doing this in my head as I go. Negative 12/2, so we have negative 12/2. 7 is 14/2, so negative 12/2 plus 14/2 is 2/2, which is 1. Nice, that works out great. And now I've almost isolated y. Again, what I don't want to do is just divide both sides by negative 5/2. I mean, I'm kind of doing that anyway, because I'm going to take negative 2/5 of row 2. Why am I taking negative 2/5 of row 2? Well, dividing by negative 5/2 is the same thing as multiplying by negative 2/5. Great, so let's do that. So we're going to take negative 2/5 of equation 2, and we're going to report that as the new equation 2. So we get 2x plus 3y equals 4, and 0x plus 1y equals negative 2/5. Now I want to use the second equation, now that I know that y is equal to negative 2/5. Again, we don't want to use substitution because that's just not what we're going to be doing for, imagine 3x3 or 4x4 systems. Don't worry, we're not going to do those by hand either way, but the algorithm that we're going to be using really just can only do these row operations by either switching 2 rows, scaling an entire row by a constant like we did in this last step, or taking a multiple of a row and adding it to another. So to use this second equation now, any multiple of it that I take and add to the first row, I'm not going to be changing the x at all because I have a 0x here. So in this instance, to cancel out the 3y, I want to take negative 3 of row 2 and add it to row 1. And store that result in row 1. That means I'm not going to be changing row 2. Row 2 is actually, in fact, done at this point. So negative 3 times 0, and I can go ahead and copy down the second row just to remind myself that I'm not actually changing the second row. Negative 3 times 0 plus 2 is 2. Negative 3 times 1 plus 3 is 0. And negative 3 times negative 2 is 6. 6/5 plus 4. Go ahead and just do that real quickly here in my calculator. 6/5 plus 4. I'm going to convert that to a fraction just to keep everything as exact as possible at this point. Comes out to 26/5. Now I'm almost done. I've already solved for y in the second equation. X, I know that 2x, that double the value of x, is 26/5. So if I take 1/2 of both sides, that will allow me to get x. So I'm going to take 1/2 of row 1, and I'm going to store that result in row 1. Perfect. So 1/2 of 2x, put my 1/2 here. 1/2 of 2x is 1x. 1/2 of 0, you can see that now that we've eliminated all the y's in the first equation, that's still just going to be 0y. And 1/2 of 26/5, so that's 26 over 10, which comes out to 13 over 5. And 0x plus 1y equals negative 2/5. So we're done here. We've now found that the solution, xy, is x is 13/5 and y is -2/5. Or we could write this as a vector, 13/5 on top, -2/5 on the bottom. And we've just found the intersection point. Remember that all we've done now is just we've figured out that these two lines will intersect over here at 13/5, -2/5. Somewhere down here, our two lines will intersect. Same thing over here. Also, one important thing to note is if this were a matrix, notice that we would have 1, 0, 0, 1. So as a matrix, this would read 1, 0, 0, 1, 13/5, -2/5. That's going to be extremely important as we move forward because we're going to be doing all of these operations instead of on equations. We're going to be doing them on the coefficients only. Because as you see, as long as we have the x's in one column, the y's in another column, and then the constants in a third column, the beauty of this process is going to be that we can just operate on the coefficients and the constants, and we don't need to actually have the x's and y's in there.